We've got some more conservation of energy in this problem. Now we're specifying that we're looking at things that move under the influence of springs, or at least stretchy things. For this one, we're going to look at a bungee jumping problem. Now, bungee cords and rubber bands and elastics, those don't really behave quite like springs. The spring constant thing doesn't quite work out. It actually changes, so it's pretty easy to stretch a rubber band for that first inch or two, and much tougher to stretch it for those next couple inches. And that happens with springs too, but to a lesser degree. So we're just kind of going to pretend that bungee cords behave like springs, and that we can still use Hooke's law and say that distance stretched and the force are proportional to each other. It doesn't really work out that way, but this seemed like a fun problem to do. Also, the question in this one is basically, does this person survive the bungee jump? Are they going to hit the bottom anyway? And so I thought I'd add a little extra suspense here, and I haven't solved this one out, so I don't really know. This person may suffer a really terrible fate. So in that spirit, go ahead and cue the dramatic music. All right, well, that's sort of dramatic, I guess. Well, let's go ahead and figure this one out. So we've got two moments in time when he's standing up on the bridge or the platform or whatever. It's about to jump, and then the next moment in time where that we're going to look at is once that bungee cord is stretched as far as it stretches. The person is dangling at the end of the taut bungee cord. They've just stopped moving at this point. They're about to start moving back upward, and hopefully there's still some distance between our little bungee jumper's head and the ground here. So let's find out. Like I said, this is a conservation of energy problem, so we'll start out the same way that we usually do, with total energy initial is equal to total energy final. And I'm going to try and be consistent with how they notate things on the AP exam, so we use the not symbol instead of the I, and no F for final. So total energy at the beginning is equal to total energy at the end. So what energy types do we have at the beginning and at the end? Well, initially, this person's up really high, so we've definitely got some gravitational potential energy at the beginning. And not moving, and the bungee cord isn't stretched out, so no kinetic energy, no elastic potential energy, so just that gravitational potential at the beginning. And at the end of our problem, like I said, he's come to a stop at this point, so no kinetic energy here. Hopefully still has a little distance between him and the ground, so we'll assume there's some gravitational potential energy there. And this bungee cord is all stretched out at this point, so we've got elastic potential energy there as well. So we'll have gravitational potential plus spring energy, or elastic potential energy. Okay, so let's fill in some values here. Let's get equations in. So gravitational potential energy, we'll just do mass times gravity times height, not height initial, is equal to mass times gravity times the height at the end, plus 1/2 kx squared. Okay, and if we start looking through these values, I see, I've got mass in there, which is given to me, so I can plug that in. I've got gravity, acceleration due to gravity in there, both places. So I know that's 9.8 meters per second squared downward. The initial height, I know I'll call the ground to be 0, so he starts up at a height of 120 meters. The final height, I don't know. We hope it's something more than 0, that there's some distance here, but I don't know what the value is for that. So I'm just going to make a note of that I need to figure out what this is. That's my H. And then, let's see, K is given to us here, the spring constant for this elastic rubber band. And then X, the distance stretched. Well, let's see, I don't know that one either. But I do know that this bungee cord is 45 meters long when it's relaxed. So I could think of some distance here, as being 45 meters. And then however much farther it's gone beyond that, that would be x. So I have this relationship, and I've kind of shown x going along with the bungee jumper here. Just kind of treat the bungee jumper like he doesn't have any height there, and it won't have a significant impact on our problem. So we got this relationship between x and h, which is good because in this equation I have two unknowns. This h and this x are both unknown to me. So I need a second equation if I'm going to solve this. So I know that this total distance is 120 meters. So I can also write the equation that 120 meters is equal to 45 meters plus x plus h. So two unknowns in these two equations. I know that I'm going to end up solving this as a system of equations. So let me go back to this one, and we'll plug in some numbers here. So we've got 70 kilograms and 9.8 meters per second squared, and 120 meters is equal to 70 kilograms, 9.8 meters per second squared, and h plus 1/2, 40 newtons per meter, and x squared. Okay, so you'll have to bear with me in the spirit of suspense. You're going to have to wait for me to do the calculations on this. So on the left side I get 82,320 joules is equal to 70 times 9.8 is 686, and that'd be kilogram meters per second squared times h plus 20 newtons per meter times x squared. All right, now ultimately I'm going to be looking for h, I guess, is probably the easiest way to do this. And I want h to be some positive value. I want him to have some positive height at the end of this problem. So let me just rearrange this equation in terms of in those terms so that I can plug in an expression for x into this equation and then use that to solve for h. So I'll subtract the 45 from both sides, so I get 75 meters is equal to x plus h, and then if I want x all by itself, we'll do 75 meters minus h is equal to x, and then that is going to get plugged in for x right here. And I'm running out of room, so I'm just going to move the whole thing down here. And let's see what we've got now. So we have 82,320 joules is equal to 686 kilogram meter per second squared, h plus 20, and that was newtons per meter, plus, or times 75 meters minus h, and that gets squared. Okay, so it's not a real pretty equation, but it's a solvable one, just one unknown in this one. So we'll do 82,320 joules is equal to 686 kilogram meter per second squared times h plus, let's see, 75 squared times 20 is going to give me, for my constant value, 112,500, and let's see, that would be newtons, Newton meters, so joules. That's right. And then let's see, we'll have 75 times negative h, and a 75 times negative h, so that's negative 150 meters times 20 newtons per meter times h, so that would be negative, what did I say, negative 150 times 20, so negative 3,000. And that's newtons times h. And then minus, let's see, I've got h squared, or sorry, plus h squared times 20. So 20 newtons per meter times h squared. All right, let's clean this up a little bit. So I'll move the 112,500 to the other side. And we get over here, negative 30,180 joules is equal to, I'm just going to get rid of these units. These are making this a little tedious to write. 686 H plus the negative 3,000. There we go. 686 H plus the negative 3,000. Oops. So it's negative 2314 H, and then plus 20 H squared. Okay, so now I'll rearrange this. 0 equals 20 H squared minus 2314 H plus 30,180. All right, so it's a quadratic function. I'm going to solve this one with by graphing. So 20x squared. In my calculator, I'm typing 20x squared minus 2314x plus 30,180, and I'm graphing that. And I'll just do the zoom fit. That'll help speed this up a little bit. Alright, and I see a positive root there, so I think our guy is in good shape here. So let's see, we'll have, I'm going to trace, or rather math, and then 0. I found the 0. It looks like we get a final height h is equal to about 15 meters. So yes, he survives. Just barely, but he survives.